Welcome to STEM Professionals. In this video, we'll discuss two important things. The first one, dimension of a physical quantity. The next one is checking dimensional consistency. So let's start with the video. Now in physics, when we speak of dimension of a physical quantity, we basically refer to the type of quantity. For example, we need to measure the distance between these 2 points, as you can see in this video. So the distance between these 2 points can be measured in meter, or you can measure it in kilometers. But the catch point here is that both have the same dimension, that is length. Now we can take another example. Suppose this car is running at speed 150 kilometers per hour. Here the unit we have taken is kilometers per hour. You can also convert it into meters per second or meters per minute. So if you see the unit of velocity, it is kilometers per hour, or you can take it to be in meters per minute or meter per second. You can take any unit. But if you see the dimension of the speed or the velocity, it is length over time. Now any valid formula in physics must be dimensionally consistent. That is, each term in the equation must have same dimension. Let's understand this with the example. Suppose this is one equation I'm taking. This is 4 hour plus 10 meter. It is equals to 40 hour per minute. Now this equation is totally wrong, or it doesn't make any sense. Why? Now here if you see the dimension of this quantity, it is time. The dimension of this quantity, it is length, and the dimension of this quantity, it is length over time. And here you can see that the dimension are not same for each quantity. That is why it doesn't make any sense. So let us take one more example. Suppose that x is this x represents a distance, so x equals to x naught plus vt. Now this v is the velocity and t is the time. So let us see that whether this equation is making some sense or not. Now if you see the dimension of this x, which is distance here, so this will be length. Now if you see the dimension for this x naught, this also shows a distance, so that is also length. And if you see the dimension for this physical quantity, let us see, this velocity will be length divided by time multiplied with this t is time, so this is time. So here we can see that this one will cancel it out, and here we see that length is equals to length plus, and this also is length. So this equation makes sense, and this one doesn't make any sense. So I hope you are clear with the dimension of the physical quantity. Now to check the dimensional consistency of an equation, it is convenient to introduce a special notation for the dimension of quantity. So we're going to use the small brackets to represent the dimension of a physical quantity. For example, this x denotes the distance, and we know that the dimension for distance is length. So we're going to denote it with L like this. So this will represent the dimension of distance. Suppose you can take time. So for time, this will be like this, t. Suppose you want to take mass. So for mass, it will be capital M. This is for mass. Now next in this video, we're going to discuss the dimension of some common physical quantity. So I'm going to write quantity here, and in this I'm going to write the dimension. Now the first quantity that we are taking is distance. This is a physical quantity. Now distance, as we have already discussed earlier, it is length, so we're going to denote with this notation, length. Now next we can take volume. Now volume, we know it is, if you see the unit of a volume, it is meter cube. So meter means, if you see the dimension, it will be length, so length cube. So the dimension would be L cube, like this. Now next we can take velocity. Now if you see the unit for the SI unit for velocity, it is meter per second. Now the dimension would be, the meter means this is distance, so distance we have length L, and this is second, so second we have time. Therefore the dimension for velocity, it is length over time. Now next one we can take to be acceleration. This is also a physical quantity. Now if you see the units for this acceleration, it is meter over second square. This is the SI unit. Now meter, the dimension would be length. Time, this is second, means this is representing the time, so time square. Therefore the dimension would be length over time square. So these are the dimension of some common physical quantity. Now let us take one equation, and we're going to check whether this equation is dimensionally consistent or not. So this is our equation. Here x represents the final distance of any object, you can assume. X0 is the initial distance, V0 is the initial velocity, t is the time, and here a is the acceleration. Now x is distance, so dimension for distance is L, that we studied earlier, is equals to, now x0, it is initial distance, so this is also the distance, so length plus. Now v0 is the initial velocity. Now the dimension for velocity that we studied earlier is L over t times, now this is time, so time is the dimension is t, plus, now 1 over 2 is a constant, so there is no dimension for a constant number, so we can neglect this 1 over 2. Now acceleration, so acceleration is length over t square, that we have studied earlier, and this is t square, so t square means the time square, so like this. Now here we see that this one and this one will cancel it out, this one and this one will also cancel it out, and finally we'll get that length or L is equals to L plus L. And here we see that the dimension of each quantity in this equation, sorry, I left out one L here. So here we can see that the dimension of each quantity in this equation is L. So this equation is a valid equation because each term have same dimension. Now next I'm giving one question to you for the better understanding. Suppose there is one equation, capital A is equals to A times small t. Now this small a represents the acceleration, and this small t represents time, and your task is to find out dimension of this a, and you have to write the answer for this question in the comment box below. So this is all for this video, and in the next video we're going to discuss the significant figures, scientific notation, and the round of error.